Before we begin, just some considerations that I want to talk about. When we're talking about programming real-time graphics, this stuff is hard. I'm not gonna lie to you and say that, oh, it's like easier than you think it is. It's not that bad. This stuff is complicated, and the reason I'm telling you that is not to discourage anybody from pursuing this. It's because I don't want you to get into this and run into something complicated or difficult to understand and then just go outside and kick rocks. Like, it's hard. You're going to run into frustrating stuff, and there's a lot of terminology and things to understand. One thing about rendering is that a lot of these concepts are very deeply interrelated. I'm going to be using, a lot of specialized vocabulary to talk about certain things, and I'm going to try to explain all of it to the best of my ability, but it's very hard to refer to one concept in isolation. They're all referring to a lot of other concepts. There's a lot of terminology. They're all interrelated, and I'm going to do my best to break it down, but you are just going to have to keep a lot of stuff in your head. Another thing is that this is a technical art form, so there's like elements of art and like technical craft coming into this. So like any art form, your ability to imagine things is going to go a long way. Your ability to be creative is going to go a long way. And what you're trying to do is translate your creative ideas or someone else's creative ideas on your team into, a process for getting pixels on the screen. And I think that's really cool. I think that makes this really unique. And it's honestly really fun once you get the hang of it. The other thing is that optimization is really important. Like a lot of what I'm going to be talking about today is I'm going to be breaking down these concepts for you so that when you go into like implementing an effect or something like that, you're going to understand like what makes something perform well and like what makes something not perform well. I think like any effect that you do, it doesn't matter how cool it is if it's going to run at 1 frame per second on somebody's computer. So the last thing is that I believe in you. I know I just said that this stuff is really hard, but learning anything is hard. Learning how to draw is hard. Learning how to paint is hard. Learning how to play an instrument is hard. Learning how to write a renderer is hard, but that doesn't mean you can't do it. So with that, so what is real-time rendering? Well, everybody here has probably seen, like a 3D animated movie or something. We've had them for our whole lives. Like Pixar movies, it's a technique called pre-rendering. So the idea is that you're creating computer-generated imagery. They are using giant server farms to bake these very detailed images and then play them in sequence. That's what an animated movie is. It's all pre-rendered because there's no element of interactivity. The movie is the same every time, no matter what happens, so you can do that. So when we're game developers, we don't have that luxury. Like, we have to be able to react to input at a very precise level. So real-time graphics applications is like the broader category for this stuff. That could be something like a game. It could be something more abstract like a music visualizer. And all of these things are an animation medium. So that means we have to be presenting frames continuously at, hopefully like a steady rate. The reason we need to think about real-time rendering in games is because games are interactive. So they need to react to things that the player does. So we don't have the luxury of pre-rendering stuff. We have to be able to do everything immediately. Frames have to be delivered in a timely manner. Like stutters feel bad, like frame rate drops feel bad. So we're trying to keep things, clean and steady. And that means that optimization is key. The reason I'm going to tell you about all of this hardware stuff and all this terminology is because I want you to be able to understand, at some level, I want you to understand intuitively what kinds of things are going to be efficient and perform well and like what kinds of things aren't. So we're going to go way back to the good old days of like 1991. We've got the Super Nintendo. This is a very basic diagram of the organization of the memory structure of Super Nintendo. So We have video RAM, and video RAM is going to store tiles and tables that you can build backgrounds out of, and sprites also. You have color graphics RAM, and that is going to store color palette entries, because back in the days of built-in 2D rendering hardware, you wanted to be able to palette swap easily. So they had specialized rendering structures for these things. And I'm going to talk about how we don't have those anymore later. You have object attribute memory. So these are tables of tiles that can refer to video RAM. Those are going to be what you think of as sprites. And like, if you don't know what a sprite is, you can basically just think of it as like a little, it's like a small pixelated image, basically. And we're going to compose like animations and, objects in our game out of those. Another thing to note is that this was a direct memory access architecture. So what that means is that all of these different memory units, they can communicate and transfer memory to each other immediately. On the NES, you basically had to wait for a timing interval to do any memory operations. And that meant that you had to render everything all at the same time before you could switch any memory out. And on the Super Nintendo, you no longer have that limitation. You can switch memory around, you can switch graphics modes in the middle of rendering a frame. And so that's why Super Nintendo games can do much fancier effects. So this is what we had, like, if you were programming for like a Super Nintendo or a Sega Genesis or something, it's going to be stuff like this. They have specialized hardware and memory specifically for solving the problem of rendering a 2D scene. So what about PC gaming? So that's happening around the same time. And the thing about PCs originally is that they did not have specialized hardware for rendering. All rendering calculations on older PC games were performed on the CPU in code. So you don't have any of the specialized palette swapping or like any of that hardware that enabled any of those techniques. You have to just write a program that does all of that manually, and eventually something is going to spit out pixels on the screen. So the nice thing about that is it's really flexible. PCs usually had more powerful processors than the specialized hardware, but the architecture is not specialized. So that means you have to, there's certain things that are going to be easier to do on specialized hardware in terms of performance. So some notable games that use software renderers: Doom, completely a software renderer; Descent, completely a software renderer. Pretty much any PC game made before 1995 is going to have a software renderer because graphics processing units had not been really popularized yet. And so we're going to show screenshots of some of those games in a second. Some low-spec modern games still use software renderers, actually. A great example of this is a game I played recently called Hrat, which came out this year. It was programmed by a single guy in Czech Republic, and he wrote a complete software renderer in Perl. It looks really cool. It can be a really neat technique, honestly. And the thing about modern processors is they're way more powerful than what you had in like 1993, so you can really push a lot of stuff through it. And software renderers were included as fallback renderers well into the 2000s after graphics cards had been more popularized. A lot of people still didn't have them. You didn't want the game to just crash if somebody didn't have a GPU, so you'd include a software renderer fallback. And that meant people could still play your game. They would turn off a lot of features and stuff, but it would still run, even if you didn't have a GPU. So we're going to talk about Doom. So I was going to explain the Doom renderer, but I realized that it would literally take me like half an hour. It's very complex. There's a lot going on here. The main idea of it is you have something called ray tracing. And like you might have heard that because a lot of modern graphics cards actually advertise built-in ray tracing features into the hardware. This is basically the same idea. You're treating each pixel as like casting a ray of light from the camera, and it's going to hit something eventually, and that something is going to have a color, and it's going to be affected by light sources or shadow sources, and then that's how you're going to fill in like each pixel on the screen, basically. And Doom does a lot of stuff to make that more efficient. Like they divide the level into what's called like a binary space partition, which like lets you efficiently decide like which objects are going to be intersected by light, and all that stuff. It's actually very technical and fascinating if you want to read about it. I'm not going to explain it because it's going to take the whole presentation, but that's a great example of like a 90s software renderer. Similarly, we have Descent in 1995. I love how greebly this looks. You're never going to see anything that looks like this now. You know, I think it's like these techniques are technically outdated, but I think you can still, you know, you can still artistically compose like really interesting stuff with these techniques, and it's gonna look very different from the kinds of stuff you're gonna get from like a modern rendering API. And then jumping into the 2020s, this is a screenshot of that game I mentioned earlier, Rot. It's like a Chernobyl horror kind of 80s fall of communism game, and this is a software renderer, programmed custom by one guy, and like it gives the game a really cool retro look. You know, I think one thing I'm going to talk about is how, you know, maybe I'll just mention this now. So one of the questions is like, okay, you know, why do I need to learn all this technical stuff? Because like Unity or Game Maker or Unreal, they're just going to do all this stuff for me. Like, why do I need to understand how like a renderer works? And like what I would say is that like digging into customizing a renderer or writing one yourself, it's going to give your game like automatically some visual standouts that like make it look different from what everyone else is doing. Because if you just go in there and you just pick the default Unity post-process pipeline and whatever, it's going to look like every other Unity game that does the Unity post-process pipeline. And if you're building your own custom techniques, it gives you more flexibility as an artist, and it makes whatever you're creating stand out that much more. I think this is a great example of that. So moving beyond software renders, so remember, all of those are happening on the CPU. That's where like most of the processing in your computer is happening. There's no specialized hardware. It's all just software processes. So the problem with that is a lot of graphics processes, as we can see from like the architecture of like the Super Nintendo that I showed you earlier, is that you can get really nice optimizations from just having hardware that's specialized for certain operations. And you know, that's going to let you create more complex scenes. You can do stuff like fancy dynamic lighting. There's a lot of reasons artistically why you would want better performance from these processes. And so in comes the concept of the graphics processing unit. So the GPU it's a separate processor inside your computer. And it has special hardware that is completely designed for speeding up real-time rendering, and it has built-in hardware for the kinds of processes that you're going to use in real-time rendering. So early GPUs had what they call a fixed function design. And what that means is that you're going to have functions that you call in your program, and those directly map to dedicated built-in hardware logic on the GPU. And the problem with that is like you're going to get really nice speedups from those things, but it's extremely inflexible because anything you want to do that's outside the bounds of that hardware is not going to be possible. So as a reaction to that, because basically what this means is that anything you do in hardware is going to be less flexible than what you can get with software render. So to counteract that, the shader unit was invented. Around the year 2000, this started to get popular. And what a shader unit does is it's basically, there are all of these like mini processors, basically. Your GPU is composed in these days, they would have a few shader units. Modern GPUs have literally thousands of them. And they're basically all running tiny parallel programs at the same time. And they're just shoving pixels through these tiny parallel programs. So because of that, you now have programmability, which gives you some of the flexibility back that you lost from, you know, moving away from software rendering. So the modern GPU, again, has thousands of these. They have several gigabytes of built-in memory for sampling textures in the shader unit. Shader units actually are like mini processors now, which is, you might have heard the term compute shading somewhere in terms of advanced rendering. That's literally because you just have like a tiny, like the shader unit is basically just a tiny CPU at this point. And modern GPUs will have like specialized hardware for things like ray tracing. I think it's kind of a gimmick, but there you go. Modern gaming consoles, we no longer have like Super Nintendo specialized architecture. In the old days, a PlayStation had a completely different hardware architecture from like a Nintendo 64 or a Sega Saturn or whatever. Those days are over. All modern gaming consoles are just PCs now. They literally use AMD graphics cards. The only difference is that they might have like special APIs or like a few special optimized hardware routes or something, but they're literally just PCs at this point. The days of unique computer architecture are mostly over. Yeah, so before I move on, I forgot to mention this, but if you have a question and like I'm completely losing you, feel free to just ask a question and interrupt me. Like I know there's a lot going on. Are we all good? Okay, great. Okay, so I'm going to talk a little bit. This is like the progress of like the AMD Radeon GPU architecture. Pre-2000s, you can see we have fixed functions. So there's just optimized hardware on this coprocessor, and you can be like, hey, coprocessor, like calculate some Phong lighting for me. And it'll be like, okay, and it'll give you, a color. And like I mentioned before, very inflexible, not much you can do with it outside of the bounds of those functions that have been built into the hardware. So post 2000s, we get into like the second era of like modern GPUs, which is that we have simple vertex shaders and simple pixel shaders. So that's going to give us a lot more programming flexibility over the rendering. And I haven't talked about what shaders are. This is what I mentioned earlier. We're going to have a lot of interrelated concepts bouncing around. I'm going to tell you what a shader is very soon, but just take my word for it right now. And then, moving into the later eras, you can see that the complexity of shaders increases massively. What they're capable of doing expands a lot, to the point where on a modern GPU, it's basically just like 1,000 mini processors like living on a single chip. So you don't need to understand any of this. I'm just trying to give you an idea of how much the complexity of these machines has evolved and how specialized they've become, but also how they're basically just general purpose computing machines at the same time. This is a diagram of AMD's RDNA architecture, which they introduced on their GPUs about 5 years ago. You can see that we have huge memory caches. We have individual shader engines formed of like a bunch of little compute units. They all have they all have memory that's localized to these individual processors because fetching memory is a relatively slow operation. So they want the memory to be physically on the hardware as close to these computation units as possible. So like, it's some people's, entire lives is like figuring out like how we can design hardware to just push these pixels even faster at this micro level. So again, you don't need to understand how GPU architecture works if you're writing renderers. A lot of it gets abstracted out, like unless you're going to go work for NVIDIA as like a driver writer, like you don't really need to understand any of this. I'm just trying to give you a picture of how complex these machines have become. So now that we have GPUs, we have another problem, which is you need to be able to interface with this specialized hardware, right? So by 1997, we had so many video card manufacturers. We had S3, ATI, Matrox, PowerVR, 3DFX, Rendition. All of these are individual manufacturers making individual products. So as a programmer, imagine having to support all of those individually. You're like, I'm going to write a PC game, so I have to write a renderer that works on ATI and Matrox and PowerVR and 3DFX. Otherwise, people can't play this game on their computer and they get mad at me. So as a result of this like increasing fragmentation problem, in the early 90s, kind of at the dawn of all of this, Silicon Graphics Incorporated, which is another one of these companies, they open source what they call their Iris GL standard, which becomes OpenGL. And what this is it's a standardized hardware, or sorry, it's a standardized software API. So what that means is ideally, you as the programmer writing a renderer, you write your code to the OpenGL specification. Then it's somebody else's job to translate the OpenGL calls that you're making into the lower level functionality of that hardware. So you don't have to understand how a 3D card is different from a PowerVR card. You just write some OpenGL code, and then somebody else worries about making sure that the OpenGL code runs correctly on all of these different fragments of hardware. In 1996, Microsoft releases Direct3D, which you've probably heard of. That's like was the main competitor of OpenGL for a long time. In 2006, Silicon Graphics transferred control of the OpenGL API to a group called the Kronos Group. And the Kronos Group is a nonprofit consortium of all of these dozens of industry stakeholders. So that would be people who are writing graphics drivers, people who work on operating systems, people who work on actually manufacturing this GPU hardware, game developers, game engine developers. All of these people are part of the Kronos Group, and they work together to refine this open standard, basically, and make sure that people are conforming to it in a way that's not going to lead to weird fragmentation problems. If you have fragmentation, then, as an engine developer, now you're thinking, I have to think about all these hardware quirks, and you don't want to do that. That's a bunch of work. So we're all going to work together to try to limit the amount of work that we all have to do together. In 2016, the Kronos Group they released the Vulkan specification. So Vulkan was originally going to be like the redesign, the sequel of OpenGL, and that was mostly work being done by AMD, who is the #2 GPU manufacturer in the world right now. They were working on a new graphics API they thought would make things easier for developers to work with their hardware. They eventually ended up giving all of that research for free away to the Kronos Group to release as an open specification. So if you've heard about Vulkan, that's what it is. The design of Vulkan ended up influencing a lot of later APIs. We have Metal by Apple. We have Direct3D 12, which was like a complete redesign of Direct3D. So what I'm getting at is that now, today, we have several graphics APIs. We've got Direct3D 11, we've got Direct3D 12, we've got OpenGL, we've got Vulkan, we've got Metal, we've got whatever crap Sony is doing. So that's starting to sound familiar, right? Doesn't that sound a little bit like fragmentation? Yeah, because now you're not thinking about, I'm going to target specialized hardware, like, I need to make sure my code runs on AMD and NVIDIA. Now you're thinking, my code has to run on Direct3D 11 and Direct3D 12 and Vulkan and OpenGL and yada yada. So as a result of that, we now have the evolution of intermediate graphics APIs. So you see how we just keep creating problems for ourselves? So now we have at least 6 graphics APIs in widespread use. As a programmer, imagine having to support all of those. I do. It sucks. So graphics APIs, the thing about graphics APIs is they're broadly similar, right? Like, the fundamental processes of rendering are not that different. There are certain things that you are just always going to do and need to do. So these interfaces are, they have a lot of the same characteristics, but maybe they'll just change a little terminology here and there. The way you call a certain, function is a little bit different on this API. So if you're a developer and you're interfacing directly with these APIs, it's really annoying because now you have all of these different routes that you have to follow. So an intermediate API is something that sits above that and basically provides a standardized layer for you to write code, which will then be translated into these underlying graphics implementations. So you don't have to think about on my GL renderer, I'm calling like a GL binding function, and on Vulkan, I'm calling a Vulkan binding function. You just say, hey, intermediate graphics API, bind a texture for me, and then the intermediate graphics API says, okay, and if you're running on Vulkan, it calls the Vulkan function. If you're running on OpenGL, it calls the OpenGL function, and now you're not dealing with fragmentation at the high-level game development programming level. So you write rendering code once, now it has all this cross-platform capability, because what's the problem? The problem is that if you want your game to run on Apple OS X, well, like you can't use Direct3D. It doesn't run on Apple. You have to use Metal. And so the fragmentation creates problems for you. This is what the intermediate graphics API solves for you. So this functionality nowadays, there are like a million of these libraries. I see a new one like growing in my yard after spring rain like every day. So I worked on one. It's called FNA3D. I worked on that closely with like 2 other people, and that was basically an intermediate graphics layer that we developed for the implementation of FNA, which is like it's an open source re-implementation of the Microsoft XNA library, which is very popular with indie game developers in the mid to late 2000s. So that's primarily a preservation project. We want those games to be able to survive into the future. And so we have to do all of this graphics management for modern computers. There's a game framework that you may have heard of called SDL. It's used by a lot of different games and game engines. Those maintainers are working on a intermediate GPU API, basically, that's going to provide a lot of this functionality, hopefully soon. There's one called Sokol that's fairly popular. There's like a million of these, like they're seriously everywhere, and they mostly are trying to solve the same problem, which is how do I get my code to run on a lot of different platforms without having to write a specialized renderer for every single graphics API in existence. This functionality can also be bundled into an engine, like this is what Unity and Unreal do for you. They write the low-level rendering stuff, and then you're just interfacing with the engine's rendering system at like a higher level, and they're translating it into OpenGL calls, or Vulkan calls, or Direct3D calls. Is that all making sense so far? Great. There's a blank slide. I don't know why. Maybe let's all just take a breath. Rendering. Okay. I'm gonna take some tea. Okay. Yep, that's right. Yep. So we're gonna get back into hardware land. So I'm gonna talk about something called an execution timeline. So what I've mentioned is that your CPU is completely different hardware from your GPU, and you would call that like a co-processor in like computer hardware terminology. You have like separate processors running kind of in parallel, and these are specialized. These things do not operate on the same timeline. They're not synchronized. This is very important. So most rendering related operations, like when you're in your game renderer and you're calling like a draw function, that's not going to the GPU and the GPU immediately does whatever draw call that you've made and then kicks control back to the CPU. That would be really slow. It would mean that your CPU would have to be waiting for the GPU to finish stuff all the time before it could continue executing. And that is a huge time loss. It would be very inefficient. So instead what it's doing is saying, hey, GPU, when you got some time, could you render these triangles? And then it just keeps doing whatever it's doing. So if you have to wait for another processor to finish doing something, that is called a synchronization point. You never, ever, ever want these. They're horrible. They're going to make your game run like crap. You never want one processor to be waiting for another one to finish because you don't know when it's going to happen and you're losing tons of time. It's literally just sitting there. So I have some diagrams here, and so we're going to talk about GPU bound versus CPU bound code. So you can see here we've got our CPU timeline, and the frame. It's updating all of these objects in your game, and then it's sending a bunch of draw calls, and then it's translating those draw calls into API calls, and then the GPU starts rendering. And maybe the GPU finishes rendering like halfway into the CPU updating the next frame. That means that the GPU is just sitting there. It has nothing to do the whole time until the CPU tells it to do more stuff, right? So that is what we would call CPU-bound code. That means that the GPU is finishing its work much earlier than the CPU is finishing its work. And then conversely, we have GPU-bound code. So if the GPU is taking a really long time to execute these rendering functions, that means that the CPU is just maybe sitting there for a while until the GPU finishes doing a frame. So that's when the GPU has significantly more work to do than the CPU. That means that you are GPU bound. And so when you're optimizing, you need to be very aware of whether you are CPU bound or GPU bound. Because if your game is GPU bound and you're optimizing a bunch of stuff in your game's update code, it's not going to do anything. Your frame times are going to be exactly the same because the GPU is just waiting around for stuff to do. So you're not going to get any increased performance, and the same is true of the opposite when it's GPU bound. The Vulkan API's big idea is that they were trying to separate CPU work from GPU work at a very low API level. So what that means is, I'm going to get into this, but the idea is that you want the CPU to just be able to keep on trucking all the time and like never wait for the GPU to finish doing anything. And that's going to make your performance way better. That was their main idea with that structure. So I'm going to talk about that. So we have a concept called the command buffer. So this is like a new idea in like newer modern style graphics APIs and old style APIs, Direct3D9, OpenGL. All graphics state is completely global. So when you tell the GPU, when you tell Direct3D9, hey, set the rasterizer face culling mode to forward. It's going to be like, okay, and it does that for the whole entire program. Any future draw calls that you do are going to have that setting stick until you change it explicitly. If you know anything about programming, you know that graphics global state is very difficult to manage. It can cause a lot of problems for you when you forget about certain things being set. This is the cause of a lot of bugs. So what I'm saying is that commands in these APIs, they're immediately changing the global state of your renderer anytime you do anything, and it's a lot to keep track of. It also means that you can't multi-thread anything, right? Because the state is completely global. So if you're like, oh, I'm going to do some shadow computations on a separate thread, you're going to have to gate those things to make sure that no calls are being made simultaneously, because all of the state is global. Anytime you change something on one thread, it's going to be changed on every other thread that's currently executing. That's called a race condition, and it's really bad, and it's hard to deal with. These APIs also, especially OpenGL, they perform extensive error checking on all commands. So it's constantly validating that what you're doing is correct. That is a huge performance hit because every time you're doing anything, the underlying APIs have to be like, oh, did you copy something into a buffer that was too small? Are these states in conflict with each other? I'm going to check all of that stuff for you all the time. So if you've written a correct renderer, that's a complete waste of time because you already know that it's doing the right thing, but it's still just validating everything for you. So in contrast, we have modern style APIs. So you got Vulkan, Direct3D12, Metal. These are like the new ones. I say new, but they've been around for like 6 or 7 years at this point. So in these APIs, all of the graphics state is localized into a structure called the command buffer. And so that means anytime you do anything rendering related, it's going to be inside of a command buffer. So what that means is that those commands, you're basically bundling them into this big package. And then when it's done, when you're done building this command buffer, you ship it off to the GPU and it starts grinding on whatever you told it to do. So that means that all of the state is localized. You can now do multi-threading because you could have one command buffer in one thread and another command buffer in another thread, and they're not going to compete with each other to set the graphics state. They're completely individualized. And then when you send them to the GPU is going to decide for itself what order it should execute those operations in. It's much easier to keep track of the state of the program. You're never going to set a setting that just clobbers everything else in your whole renderer accidentally. And the other nice thing about these APIs is that they do error checking on a separate layer. So you can just turn it off if you're like, yeah, I'm pretty sure this is running correctly. You turn it off, you don't get any of the performance hit of error checking, which is really nice. Any questions about the command buffer? Great. I promise this is going to get less dry soon. So now we have graphics resources. So this is like these are like the structures, like the fundamental data structures of your renderer. So the most fundamental one is a buffer. A buffer is literally just a container of data. That data can be anything, but most of the time we're going to be representing concepts like vertices and indices. I'm going to talk about that. You have textures, which are basically containers of pixel data. You have samplers, which tell shaders how to reference textures. You have shaders. There's two kinds of shaders that you're going to use in the graphics pipeline. It's a vertex shader and a fragment shader or a pixel shader. Vertex shaders transform vertices, and pixel shaders transform pixels. And these are always one-to-one, so I'm going to get into that more. And then finally, a pipeline is going to bundle all of these things together, and the pipeline is going to be how you get from a buffer and a pipeline configuration to finally what our goal is, which is pixels on the screen. So buffers contain data. That's it. You got vertex buffers. So a vertex is a point in space, so it always has a position of some kind. Vertices can have auxiliary information attached to them, so you might be like, okay, this pixel is, this vertex is red colored, and this vertex is blue colored. And each individual vertex can have an individual color or an individual texture coordinate, and you can attach all kinds of useful data to those things. And then vertex data, like a big set of vertex data that forms a set of triangles, is called a mesh. And the reason we have index buffers is because that allows us to repeat vertices without having to duplicate the data, which saves a ton of space. So I think I might want to diagram this, actually. Say we want to draw a quad, which is just two triangles in the shape of a rectangle. So that's a rectangle being formed out of two triangles. Let's label these vertices. So this is vertex 0, this is vertex 1, this is vertex 2, and this is vertex 3. So let's say that I'm not using an index buffer. So that means we have two triangles, right? We have triangle 0, 1, 2, and we have triangle 1, 2, 3, right? So you'll notice that vertices 1 and 2 are being repeated twice. So if we lay this out sequentially, we have the data for vertex 0, 1, 2, 1, 2, and 3, right? So this is completely redundant information. So how do we get rid of that? We use an index buffer. So the index buffer is basically saying, okay, when you need vertex 0, so your triangles are actually going to be listed out in here. So this is an index buffer that's telling you, okay, render triangle 0, 1, 2, and then render triangle 1, 2, 3, right? And then what it's going to do is it's going to look into a vertex buffer which has all of the data for vertex 0, and all of the data for vertex 1, etc., right? So now we're not duplicating all of that data. Like, in the case where we only have position, this is not a huge time saving, but like, what if you have color attached to a vertex, and texture coordinates attached to a vertex, and like all kinds of other metadata on it? You're repeating all of that data. It takes up a huge amount of memory, especially when these meshes get more complicated. This is just two triangles. But like a modern like character model for like a AAA game is going to literally have hundreds of thousands or millions of triangles on it. And so all of that data repetition adds up really, really quickly. So that's why you have an index buffer. Does that make sense? Cool. So the thing to note, oh, yeah. Oh, okay. It is on the GPU. So what you're doing is you're building command buffers in a multi-threaded way. So when you're building your frame, what you're doing is you're submitting a bunch of commands into one or more command buffers that you then ship off to the GPU. It's basically like you're just giving the GPU like a task list, and you're like, I don't care exactly when this is done, but just like get it done, right? And then it ships it off to the GPU, and now the CPU can keep on trucking, building the next frame immediately without waiting for the GPU to finish rendering. You want these operations to be happening in parallel as much as possible. So if we go back to the execution timeline slide, like all of this idle time, that's inefficient. We want as little idle time as possible. So what the command buffer lets us do is it lets us build a bunch of commands for the GPU to do without having to wait for the GPU to actually do that stuff. So the reason you would multi-thread build command buffers is because that way you can build the command buffers faster so that you can get on to whatever you're doing. So it's not like you're actually rendering that stuff on the CPU, it's that you're building the commands for the GPU to run in a threaded way so that you can get on to other stuff. So the last thing I was going to mention about buffers is that you have to be aware of data upload timing considerations. So basically what that means is when you're building these graphics resources, they're living in the memory of the GPU, right? And so you have to get that data into the GPU somehow, right? Like at some point you have to stick that stuff in the GPU memory. But remember that the CPU and the GPU are on completely different timelines, right? So I'm gonna get into this in a little bit. There it is. Okay, so yeah, after I talk about buffers and textures, we can talk a little bit about synchronization and making sure that your data is actually what you think it is. But just know that whenever you're pushing data to a buffer, that operation is not necessarily happening immediately. And the state of your memory on the CPU and the GPU are not always going to be exact. So textures. Textures are actually a lot like buffers because they're just containers of data, but they contain data of a pixel variety. And remember, pixels are the fundamental output unit of rendering. So when you are rendering, you have just like a container of pixel memory, and eventually you want those to be filled in with colors, because what are we doing here? We're trying to flash pretty lights at people, right? So, you know, like what's the point of all of this? It's that we want colors to show up on the screen, right? So a pixel inside of a texture is called a texel. And you might be thinking, like in certain rendering processes, you might be thinking about certain operations happening in texel space, which is just in relative terms to a texture that you're dealing with. Textures have a format, and basically the format describes the color channels and then the bit count of those channels. So the most common would be RGBA. If you're like an artist, you probably understand like that an image on a computer, like a color, you have like a red channel and a green channel and a blue channel, and then an alpha channel, which can kind of just be arbitrary data. And then you're mixing all of those channels to get like a final color, basically. So what you can do is you can specify different color formats to create textures in, and like this can be a big optimization. Sometimes you don't need 3 of those channels. Sometimes you just need 1 channel, and you can save a ton of texture memory by just defining something as like an 8-bit R channel texture instead of using all 32 bits for stuff that you don't need. So picking the right format is a huge optimization. That's one of like the first things you should be thinking about if your texture memory usage is ballooning a lot, that maybe you can optimize that. One thing I didn't mention here is that some of these formats can be compressed in memory. So one mistake I see a lot of people make is like you look at like a PNG file on your like Windows desktop, right? You're like, well, that's just 800 kilobytes. So it's going to be 800 kilobytes in GPU memory, right? Wrong. PNGs are compressed. So if you want to actually render that data and deal with it in memory, you have to decompress it. And that means that it's going to take up all of that, you know, if your image is 400 by 400 and it's RGBA data, that means in memory, it's always going to be 400 times 400 times 32 bits of memory. It adds up. So the memory that a file takes up on your desktop is not how much memory it's going to take up when it's decompressed and in your video memory. Some formats can be compressed in memory. The state-of-the-art one now is called BC7, and a lot of modern GPU hardware supports that. And basically what that means is that instead of unpacking an entire texture into memory, you can put it in the special compressed format, and it'll be about 75% smaller than like a complete texture, so that can be a nice way to save on texture memory. We also have depth formats, so textures can be either in a color format or a depth format, and we're going to talk about why you use depth formats in rendering, but basically that's just going to be one 16-bit or 32-bit like decimal value. I'm going to per pixel, and I'm going to talk about why you use those in a second. Textures are written to in different ways. How does memory get into these textures? Well, you can upload it from the CPU. So if you have like an image and you're trying to render it as a texture in your game, what your loader is going to do is it's going to take the PNG data, it's going to decompress it into like a linear format, and then you can submit it to the GPU and say, hey, put all of these bytes in this texture memory. Now you have the data in that texture. You can copy textures to other textures, which is another way to fill a texture, or you can render into a texture directly using a graphics pipeline. So there's 3 ways data gets into a texture. Now with textures, you have even more timing considerations. Just like uploading buffer data, these things are not going to be completely synchronized. And I'm just going to talk about that right now. So side note about synchronization. So if you look at this pseudocode I have on the left here, we have a graphics device. We tell it to set a vertex buffer, which means that it's available for drawing. We tell it to draw the data in that vertex buffer, and then after that, immediately, we add new data into that buffer. So that seems pretty straightforward, but that is the stuff of nightmares, because, again, the CPU is on a separate timeline from the GPU. So what does that mean? You set this buffer, you tell it to draw with that buffer, now you're immediately updating that data, right? So what's the GPU going to do? Maybe it hasn't gotten around to drawing that draw call yet, right? And so if you're changing the data, that means that the data is going to be different when it finally does get around to processing that draw call, right? It's all asynchronous. So what can you do about that, from a renderer? One thing you can do is you can just stall the pipeline until the draw call is complete. That's really bad, right? That is what we call synchronization point. And that means that your CPU is not capable of continuing rendering the frame or submitting draw calls or getting around to processing the update of your next frame. It can't do any of that because it's waiting on the GPU to finish whenever it decides to finish, right? That's bad. We're trying to avoid stalling these timelines as much as possible. You can ignore the problem. You could just say, hey, like this guy, who wrote this probably knew what they were doing, and we'll just actually just run the draw call whenever, and it'll just spit out whatever. So this kind of stuff is where, I don't know. I should have included a screenshot of this. We call it like vertex barf sometimes. That's where like you see a bunch of crazy lines like drawing everywhere on the screen. It's a complete triangle mess that doesn't make any sense. That's probably because of something like this, where the vertex data changed and it just kept on trucking and it just drew it even after the data changed. You could throw in exceptions. You could say, hey, I'm not going to let you change the data in this buffer after you've submitted a draw call. You can't do that. Sometimes that's a good idea. There's like reasons why you would decide to do that. For example, in Vulkan, again, more terminology that I haven't explained yet, but after you've started a render pass, it does not let you upload data during a render pass. That gets rid of a lot of these problems because you can't actually change buffer data while a render pass is happening. So sometimes that's a good idea to structure things that way. It forces you to make sure that all of your data is like stable and uploaded before you're actually in the rendering process. You could also internally perform some magic. This is something that XNA did for you, actually. So when you draw a vertex buffer and then you change the data in it, what it does is it internally allocates a new buffer, which is the size of the original buffer. It copies all of that data over. It actually updates the copied data, and then it swaps the references for you internally. So that buffer that you're setting data on is actually a completely different buffer internally from the buffer that you set originally. And that means that you're not clobbering data in the middle of the GPU drawing. It gets around that problem. So that's like another thing that renderers can do internally. Like we have to implement this behavior on like every FNA 3D renderer because of this. So that's just an example of like a synchronization issue that you can have. Basically, just knowing that when you are telling the GPU to draw something, it's not necessarily doing that immediately. Your CPU is not just waiting around for the draw call to finish. It's going to keep on trucking. It's going to keep on clobbering data and uploading stuff and whatever you told it to do. It's not going to stop. So you have to think about that kind of stuff. Any questions? All right. Samplers. So a sampler defines how a texture is going to be read inside a shader. Remember, like the texture is just a bunch of data in memory, and the sampler, you're gonna say, hey, like sample a pixel at, you know, this coordinate, 0.2 by 0.6 or something. And then the sampler is going to define what color actually comes out of that based on the texture and the configuration of the sampler. So the main usage of this is filtering. So most GPUs support a nearest filter mode and a linear filter mode. And you can define those separately for whether the image is being downscaled or upscaled. So if you have like a high complexity image and you're upscaling it, like a linear filter is going to look better. It's going to try to blend because you're extrapolating new information below up an image, right? And so the linear filter it's just going to interpolate some of those inner pixels. It's going to give you like a blurring kind of effect that sometimes looks nicer than just directly scaling it up without doing any interpolation. However, if you linear filter sprites and upscale them, it's going to look like complete garbage. They're going to be really blurry and it's going to look terrible. So don't use that. The other thing samplers can do is they have an address mode. So the range of texture coordinate space goes from 0 to 1 in decimals, right? That's what we call texture space. So what if you give it a coordinate like 1.3, right? Now the sampler needs to know what to do because you're outside of the range of texture space. And so the address mode will tell it to either repeat, which means that it's going to loop back around and go to like 0.3. You can tell it to clamp, which will just sample whatever is at 1, or if you're below 0, it'll sample whatever is at 0. There's a few other things, like in some modern APIs, you can do stuff like setting a border color. So if you sample outside of the range, you can just tell it to spit out like black or white or whatever you tell it to do. The other thing you can do with samplers is MIP mapping, which is related to anisotropic filtering. I probably should have provided a screenshot of this, but basically, like if you've ever seen how like a texture can look really blurry in the distance when you're at like an oblique angle, that's what anisotropic filtering is like meant to offset. And the way that it does that is you create a bunch of mini versions of the texture at different sizes, and then based on the distance, it's going to sample into smaller versions of those textures. You don't need to completely understand that effect, but just know, like, you know, if you want to implement anisotropic filtering, it's going to involve generating maps and then telling your sampler to sample in anisotropic. Shaders. So shaders are literally just mini programs that get loaded, and then they do one thing, and then they're done. So it's just a procedure. These procedures execute thousands of times in parallel, depending on the data that they're processing. So you have vertex shaders. So what a vertex shader is going to do, you know, we have this texture input that I was drawing out here. A vertex shader is going to run once for every vertex input. So it'll take that position and you can transform it into a different coordinate space. You can modify the data in the vertex shader. You can distort it in some way if you want. That's what the vertex shader is doing. You can think of a vertex shader as running once for every vertex. And it's all happening in parallel. So your vertex shader is not capable of like talking to its neighbor and saying like, hey neighbor shader, what are you doing with vertex 1? I'm working on vertex 0. You can't do that because it's all happening in parallel. Pixel shaders or fragment shaders transform each rasterized pixel. I'm going to talk about what rasterization means in a second, but basically for every pixel that's being drawn, the pixel shader is just outputting a color based on some information. It's based on the information that it gets from the vertex shader and from textures and samplers that you've submitted to it. All the shader is doing is outputting a color. When you understand that, they get way less complicated to understand. One pixel is running off of one invocation of the pixel shader. Shaders can also be configured with uniform data. They're getting data from the vertex shader and from the rasterization model, but you can also pass them additional data. So for example, when you're trying to draw a light source, uniform data might be the position of the light source and the color of the light source and the direction of the light source. That's a really common way of using uniforms. It's basically, you can just, you're allowing the shader to become configurable without having to write a bunch of more specific shaders or include all of that data in the vertices. So if you didn't have uniforms, what you would have to do is you would have to attach stuff like lighting color and lighting position to each vertex, which is a huge amount of duplicated data. It doesn't make sense to do things that way. And that's why it's called a uniform, because all of that is operating uniformly on the data. Make sense so far? All right. Just a few more terms. Render passes. So basically, I talked about how textures can be written into by a pipeline, and that's what a render pass is going to define. A render pass is a set of color texture outputs. It can be 0 to 4 color outputs usually. You could have an optional depth stencil texture output, and then you have load store operations for those texture outputs. So a load op is basically saying, what should I do to this output that you're setting when the render pass begins? So we can either load the texture, so that means that whatever's already in the texture, that is going to continue, that data will be the same when the render pass begins. You can clear the texture, which is very common, like when you start a frame, you might just want to clear everything to black or clear everything to white. It'll just erase all of that data and override it with a single color. Or you can just not care. You can say, I don't care what you do with this data, it doesn't matter. The reason you might do that is if you know that you're going to be overwriting all of the color data in a texture, for example, maybe you don't want to load it, right? Because loading stuff from memory takes time. You might not want to clear it because clearing stuff from the memory takes time. So if you're just going to overwrite all those pixels, it doesn't make sense to load or clear. You can just have the driver do whatever it thinks is the most efficient thing to do. Then you have store operations, which are kind of similar. You have one of two things happen. You can either store or not care. So basically, when the render pass ends, you might want the texture to hold on to whatever you've rendered into it, and so that would be a store operation. And if you don't care, you're like, this was just throwaway data, I don't need it anymore. You can just tell it to not care, and it'll just do whatever it thinks is the most efficient. So the don't care operation, I would say, is most common when you're doing when you're rendering into a depth texture, because the depth process is just optimizing which pixels you're drawing, and you don't need that information anymore once the operation is done. So storing that data into long-term memory is going to be more expensive than just letting the driver throw it away. So any questions about render passes? It's going to make sense in a minute, I promise. So yeah, we're going to talk about, I talked a little bit about depth textures when we talked about textures. Basically, in the rendering process, we're talking about 3D space, right? Depth value is usually in the range of 0 to 1. And 1 is going to be like your far plane of rendering, and 0 is going to be your close plane, or you can reverse it. It depends on what you want. But basically, the idea is invoking shaders and writing pixels to memory is not free, right? It has to run the computations, it has to load and store memory, it has to do all this stuff, right? So one really common optimization is to just not do that. Like if you don't render to a pixel, it doesn't have to do anything. So it's a huge optimization. So the reason you have a depth buffer is if you render stuff front to back, like let's say there's like a like big cube in front of me or something. I don't have to render, like I don't want to render anything that's behind the cube, right? Because the cube that's right in front of me is just going to draw straight over it. And all of that information will be completely lost. We invoked a bunch of shaders and we wrote pixels into memory for no reason because all of that just got overwritten immediately. So that's the reason you have a depth buffer. When you have a depth buffer in your render pass, any new pixel depth that's being outputted by the rasterizer is going to be compared to the value that's already in the depth buffer. And you can say, okay, like maybe I want my depth test to pass if this depth value is closer to me than farther away, right? And so now what you can do is you can render your scene front to back, and that means that you're having as little overdraw as possible, because anything that's behind the stuff that's already been drawn, it's just not going to invoke the pixel shader. It's not going to have to update those colors in the buffer, etc. So again, that just means that drawing front to back is much more efficient whenever it's possible to do that. Anytime you draw over a pixel that's already been drawn and you replace the data, that's called overdraw. You might have heard of that. And overdraw is really, really bad on certain kinds of hardware. It's really gnarly to do that. And minimizing, just the golden rule of optimizing programs is to just not do stuff. Like, if you don't do stuff, it's cheaper than doing stuff. So if you don't have to do it, then it's cheaper. So one thing to note is that drawing front to back does not necessarily work if you have transparent objects. So like, let's say I have like a blue tinted window in front of me. If I draw front to back, I've already drawn all of that information before I draw the stuff that's behind the window. And so the colors are not going to appear to blend properly, right? And so in cases where you need transparency, you're going to have to draw back to front so that the transparency is respected. There are ways to do order independent transparency, like you can be clever about it, but it involves more thinking about it, basically. And so similar to the depth buffer, we have the stencil buffer. The depth buffer is almost always, or it literally is always combined with the depth buffer. So basically your depth buffer will have extra 8 bits appended to it, and it's a mask. So you have 8 bits. And all of this is based on bit masking logic. I'm not going to bother explaining bit masking logic if you care about it. It's it's like gnarly programmer optimization stuff where you can just like mask certain things to know like if certain values match or things like that. The pipeline sets a reference stencil value, and then it can compare that reference value. It can write that value directly into the stencil buffer, and then the stencil test process will pass if that reference value compared to the bit mask ends up being true. It'll fail if it's false. And essentially all you need to know about this is that what this lets you do is lets you carve out sections of your buffer to be rendered into. And so I'll have an example of this later in the presentation, but like, for example, if you had like if you're drawing a gun and you wanted to render like reflections out of like a sniper scope on the gun, you would stencil out that section so that then when you draw reflections, you only have to render that tiny section of the image into that stencil. So it's like a stencil cutout. That's why it's called a stencil. So breaking it all down, this is the entire graphics pipeline from start to finish. We have vertex input. What we do a process called the term is binding. So you bind a vertex buffer, you maybe bind an index buffer. That means that it's available to the graphics pipeline to grab data out of. And the vertex input process will interpret vertices from the data buffers that you've given it. It will feed each of those vertices into the vertex shader, which transforms each of those vertices. That information goes into the rasterizer. The rasterizer is essentially a process of converting the 3-dimensional information into 2-dimensional information, right? Because ultimately everything we're rendering is coming out into like a 2D pixel array, right? So I'll talk a little bit about the rasterizing process later. Once you have all of the rasterized pixels, each of those pixels is transformed by the pixel shader based on the data coming out of the rasterizer. Pixels that fail the depth or stencil test are ignored and do not invoke the pixel shader. And then finally, when the pixel shader gives you a color, it's written into the render buffer, which is like specialized texture memory. This will be like, okay, I'll put a red pixel here, blue pixel here, etc. That's the render buffer write process. That those colors are coming out of the pixel shader. So breaking it down, the vertex input. So we have like a vertex buffer, right? It's just a big list of all of the vertex data in sequential order. And the pipeline needs to know how many buffers are we binding, how should we read the data out of the buffer, and what kind of data is on the vertices. So you're basically telling the pipeline, hey, all of my vertices, they're going to have a 3D position, and they're going to have a 2D texture coordinate, and they're going to have 4 color channels for each vertex. And that way you can know the vertex or the graphics pipeline now knows how to interpret the data in that buffer. If you configure that incorrectly, you'll get a bunch of garbage on the screen. That's another cause of vertex barf, is misconfiguring the vertex input. Because if you tell the vertex input, like, hey, I'm going to give you a 2-dimensional position, and then you give it a 3-dimensional position, now all of those things are going to be offset in like really weird ways. And you're going to get a bunch of garbage on the screen. So that's the vertex input. You're defining the shape of the data that you're passing. So otherwise it doesn't know how to interpret that raw data. And then you have the vertex shader. Again, each vertex input individually is transformed by the vertex shader. Common uses of vertex shaders are transforming a mesh's local space into somewhere in the world space. You can transform a rigged mesh based on like animation bone data. If you've ever done 3D animation, that's all of those like rigging transformations are happening in a vertex shader. You can deform surfaces, like if you have like a flat water surface, you could put ripples into it by distorting vertices. All those things can be done in the vertex shader. Here's just an example of a simple vertex shader. This is taking in a 3-dimensional position and 2D texture coordinates. It's outputting some texture coordinates to the pixel shader. We are taking a view projection matrix that I'm going to talk about, and we're multiplying the position in there so that we transform the position of that individual vertex in local space. We're transforming that into screen space, right? I'm going to talk about transformations. Again, so many interrelated concepts. I'm sorry, but I just have to lay it all out like this. The rasterizer is responsible for translating 3D geometry into a 2D pixel grid. So here we have a triangle. Now that triangle is like continuous in terms of vertex data, right? But eventually it's just going to have to get into a pixel grid at some point, right? That's what the rasterizer is doing. It's basically an algorithm for taking this continuous linear data and it's transforming it into like discrete pixels on a grid. The rasterizer has a lot of different configurations that you can do on it. It can draw stuff solid, like filled in, or it could just draw the lines in wireframe mode. That's like a common debug option. You can set a cull mode. So if you think about it, like, let's say, like I have a 3D model and like I'm facing at it from this direction. The triangles that are behind where I'm looking at, the winding of those vertices is going to be reversed, right? The ones that are forward facing have a different order than the ones that are back facing. So if you've ever heard of the term back face culling, that's what that means. We don't have to rasterize stuff that is facing away from us because it's not going to be drawn. So that's culling. I'm going to do depth clipping, which is removing pixels that are too far away from the camera space or too close to the camera space. Scissoring removes pixels that are outside of a defined rectangle. So if you set the scissor area to like here, for example, none of these pixels would be passed through the pixel shader. And then you have multi-sampling, which is basically a form of anti-aliasing. You can see like aliasing are like the jaggy edges that are produced by the rasterization process, right? So like this is not like a straight looking line. It looks jaggy because of decomposing it into the pixel grid. So multi-sampling does is you sample multiple points within a pixel, and then you like interpolate the colors based on those multiple samples, so you get smoother looking edges. So next we have the pixel shader, also called the fragment shader. Again, once we go through the rasterizing process, we have all of these individual pixels, right? And so each one of the individual pixels is going to go through the pixel shader, and the pixel shader is going to assign a color to that pixel. So those transformations can be hugely varied. This is where most of the complexity comes in. You can do lighting effects with a pixel shader. You can do distortion effects. You can map textures onto a space. You can do like bump mapping or normal mapping. You could program reflection effects, blur or bloom effects. All of these things are happening in the pixel shader. And just again, these things are not executing on pixels that fail the depth or the stencil test. Finally, once we get an output from the pixel shader, we're actually going to write that color into a texture. This is the renderbuffer write process. Again, pixels that fail the test are ignored. We don't have to write to them. The main thing about this process is that you have a blend. So there might be a color already in that buffer, right? So what happens when you write a new color on top of that? That's what the blend state is going to define. It's going to define how the output is going to blend with the color that's already in the texture. This is a combination of something called a blend operation and a blend factor. So blend operations, if you've ever heard of like additive blending, that's a really common blending process for doing lights, right? Because when two lighting colors blend with each other, you want them to like add into each other and like add the color, right? You can also subtract. You can do an inverse subtraction. You can take the minimum color. You can take the maximum color value. And then those get multiplied by blend factors. I could literally teach like a 2-hour class just on blend modes. They're very intricate. I'm just skimming through it right now. But the main thing about blend modes is that you need them to execute certain effects properly, like additive lighting. And you can also, with a clever blend mode, you could cheaply avoid like having to do some like extra pixel shader processing to blend. There's some effects that you can't define with blends, like if you've ever been exposed to the concept of blending before, it's probably through a program like Photoshop. Like when you have layers, you can set different blend modes on the layers so that they'll interact with layers behind them in a certain way. That's basically a blend mode concept, but with the built-in GPU hardware, they can't express like all of the Photoshop blend modes. Like they have some abstract ones like hard light and soft light and like whatever. Those don't always cleanly map onto blend modes. You would have to write those specifically in a shader. But if you can ever do a blend mode instead of a shader blend, it's way cheaper. So do that. So breaking it all down into a basic rendering structure, we're going to, anytime we're drawing any pixels to the screen, we're going to follow this process. We're going to start a render pass, which involves saying, okay, I'm going to draw to this texture, and I'm going to use this depth texture with that, and it's going to load the texture into memory before it starts rendering. You've defined all of that stuff in your render pass structure. You bind a graphics pipeline, which is that whole process that I just talked to you about with going from vertex input all the way to pixels in your output texture. You bind resources into that graphics pipeline. So you're saying, okay, graphics pipeline, use this vertex buffer, use this index buffer, use this texture, use this sampler. And then finally, you're going to do a primitive draw call. And a primitive is what you've defined in the pipeline. It's usually either going to be lines or triangles. Triangles are the most common. You used to be able to do point rendering, but they got rid of that because it sucks. So you're going to tell it like, hey, now that you've bound all of this stuff, you tell it, hey, like draw 2 triangles. And then it will look into the vertex buffer. It'll draw 2 triangles from the vertex buffer. And then you can continue on your day. Once you're done with that, so inside of a render pass, you might bind a graphics pipeline, you might bind different resources, you might draw primitives multiple times inside that render pass, and then you will finally end the render pass when you're done with that. So the main idea is that you don't want to start a bunch of useless render passes. If you're drawing a bunch of data into the same texture all at the same time, you want that all to be inside of one render pass, because ending a render pass involves writing memory back into long-term storage and then like loading it back into short-term storage, which is expensive. Modern AAA games can actually have like hundreds of render passes in their renderers. Like they'll do like 400 or 500 render passes or something. Like that's only going to run efficiently on higher end hardware. You know, I mean, like with me and Bo's game, like people are mostly running this game on like IBM ThinkPads that they excavated out of an ancient Egyptian tomb or something. So those things can only handle like maybe like 10 render passes. So that's something you got to think about. But if you're targeting high-end hardware, you don't really have to worry that much about this. But it's always more, again, it's more efficient to not do stuff. So that's why you want to bundle as much stuff into the same render passes as possible. And then doing bindings is like a little bit cheaper, but again, you want to batch this stuff. So you want to do as much stuff in the same render pass as possible. You want to do as much stuff in the same graphics pipeline at the same time as possible. You want to do as much stuff with the same resources bound. And that's going to make your rendering process as efficient as possible. Switching stuff is always going to be an operation that takes time. Finally, like a few thoughts about math before we take a break. Linear algebra is your friend with this stuff. Like if you want to understand rendering, becoming at least familiar with how linear algebra operations work, or at least what they output is going to help you a lot. You don't need to understand all of the math behind it, but if you just know, like, hey, if I multiply a matrix by a vector, this is going to happen, knowing that is enough to get you really far. The reason we use so much linear algebra in rendering is because a lot of these concepts that we use in rendering map directly into linear algebra concepts. So, for example, light. You can think of light as a vector. And a vector is basically just like a direction in space. You can also use matrices to transform positions and directions in space. That's a linear algebra concept. It's super useful. And we're also doing a lot of projection in rendering. And so projection is the process of transforming one coordinate system into like the same information, but in a different coordinate system. That's a huge amount of stuff we're going to be doing. So speaking of that, transformations. So remember, when we're uploading data to the GPU, that takes time. You want to do that as little as possible. So when you're rendering stuff in your world, it's like not always going to be in the same position. It's going to move around based on the position of like your camera concept, like other things. And so actually having to transform all of those vertices in your buffer directly is going to be really expensive. So you don't want to do those kinds of calculations on the GPU constantly if you don't have to. So like if you had like a 3D model of like a character with like, 400,000 triangles in it, updating the positions of those triangles on your CPU is going to be much slower than doing it in a vertex shader, right? Because the vertex shader can translate each of those positions individually in parallel much faster than your CPU can do all those transformations sequentially. Certain kinds of transform operations, you have translation, which is just like the position in space. You have rotation, which is rotation in space, or scaling, which makes stuff bigger or smaller, farther apart, closer together in space. All three of those operations can be represented in one 4x4 matrix. We call that the transform matrix. It's also known as the model matrix. So you want to bundle these operations together, and then what you can do is you can give this matrix to your vertex shader, and then your vertex shader can perform all of the spatial transformations that you need for that object to appear in world space rather than local space. So talking about coordinate systems, we've got local space. So that's like the base vertex coordinates of your object. Like if we go back to my little simple quad triangle thing here, we could say that this vertex is at position 0, this vertex is at 1, 0, this position is 1, and this is 1, right? So all of these are two-dimensional coordinates, right, in the local space. So what if I want to render this quad? here, right? So what I could do is I could go in and say, okay, like this vertex's position is now, you know, 5, -2, and this one is now 6, -2, and this one is now, I don't know, I can't do that. You could update all of these vertices in the buffer directly, right? But that's going to be way slower than letting a transformation do that for you in a vertex shader. It's going to do all of these transformation operations at the same time instead of the GPU doing it one by one after the other, right? So we call this transformation going from local space to world space. And like world space is just placing all of the objects in your scene in a relative position to world origin. We also have a transformation into view space, which is like a camera's eye view. So you could have all your objects positioned in world space, but then, you know, your camera is looking at the scene from over here. So that's another transformation you have to do, right? To get everything relative to the camera. That's another transformation matrix. Then you're getting everything into clip space, which is what we call the 2D coordinates from -1 to 1. And that's just everything that's going to be rendered into your texture. And then finally, you have screen space, which is, again, 2-dimensional, similar to screen space, but the coordinate range is in terms of the pixels in your output texture rather than an arbitrary -1 to 1 range. So the main thing you have to think about is you have to be aware of these different uses of coordinate spaces in your shaders, because if you think something is in world space, but it's actually in view space, now your calculations are going to be wrong, right? Or if you think something is in local space, but it's actually in clip space, your calculations are going to be wrong. So you just have to be aware of like what space that you've transformed all of the data into so that you can operate on it correctly. We're going to talk about that a little bit in terms of calculating lighting and stuff like that. So here's an illustration of space transformations. So you have your base object data in local space. You pass that through a model matrix. Now you have all these objects in relative positions in world space. And you transform it through the view matrix of the camera. Now you have those objects that are relative in view space. Then you can put that through a projection matrix because, actually that's in my next diagram. That gets into clip space. Then we transform that through the viewport, and now we have stuff in screen space, and this is what's actually going to be in the relative pixel space of your output texture. So there's two main kinds of projections that get used. There's an orthographic projection and a perspective projection. Orthographic projections, I would say, are generally used in like 2D games because they compress. It's fine. Perspective space is what you use mostly in like 3D games because you want everything to be in perspective and you want like this illusion of depth and stuff like that. So you have like a field of view, you have a near plane, you have a far plane. Everything is getting distorted, right? Because again, all of this data is in 3-dimensional space. And ultimately what we're doing is we're drawing this stuff in a 2D space, right? Your computer monitor is 2-dimensional. So at some point, we have to distort that information from 3 dimensions into 2 dimensions. That's what the projection matrix is responsible for. So on that note, let's take a break. We've been talking about all the terminology and the history and the architecture of all of this rendering stuff. And now I'm going to show you how we actually make specific effects with this stuff. So just a quick terminology review. We have rendering APIs, which are layers that translate higher level code into actual instructions on the GPU. We have buffers, which are a memory container for data, usually vertices or indices. We have vertexes, which are points in space that have additional data attached to them. Shaders, programs that execute in a massively parallel fashion on the GPU. We have textures, which are memory containing pixel data. Render buffers, textures plus metadata that we render into with a graphics pipeline. Graphics pipeline is a configurable process which transforms our buffer data into pixels in the render buffer, frame buffer. And then matrices are 4x4 grids of numbers that can represent multiple operations that transform vertices. So we're going to talk about some different graphics techniques that you can do by putting all this stuff together. So In the early 80s, we have a very basic lighting model, which is called the Phong model. It was invented by a computer graphics scientist named Phong. And the idea of the Phong model is that anytime you're talking about an object being lit, we can break that down into certain specific components. So, we have ambient lighting, because objects are never really completely dark, right? Like even in a mostly unlit space, you might still have lighting from like outside a building, or the moon in the sky, or the sun, or whatever. That's ambient lighting. You can actually calculate ambient lighting using some fairly complex techniques that you might have heard of, like global illumination or things like that. That those involve fairly intricate pre-baking processes to make the ambient lighting more accurate. But in a simple Phong model, that can just be a single color. You just pick a relatively dark color, that's your ambient light. Diffuse lighting, that represents the directional impact of the light. So you can see in this diagram, we can imagine the light source like being over here, and it's projecting onto this cube. And so one face of the cube is more lit than the faces that are facing away from the light source, right? That's diffuse lighting. And then finally, we have a specular component, which is like the shininess from a light source, which is going to change based on the relative distances of the object to the light and the object's material, right? So what you want it to look like, it's going to be more shiny. Some things are more shiny, some things are less shiny. That's your specular component. And when you put it all together, you get this combined, really nice, natural-looking light, and that's called Phong shading. So a lot of things use this. A lot of things still use this. It works pretty well. And so I took the liberty of writing a Phong shader. You don't really have to understand all of this, but the gist of it is that we have some vertex inputs. So our vertices have obviously a position, and they have an input color and an input normal vector. A normal vector is just a vector that is projecting out directly perpendicular to a surface. And then we have the position of the fragment in space, and we're trying to get a color out of all of this, right? So our uniform data is going to be the position of the light source, the color of the light source, the view position of the camera, an ambient light color, the strength of the ambient light color, and then the strength and shininess of the specular component, right? So when we put all that stuff together, we can calculate the ambient color by multiplying the ambient strength of the light by the light color. Then we calculate diffuse lighting by taking the normal vector coming out from the object. We normalize that, and then we compare it to we take the dot product of that normal vector with the light direction, and that's going to tell you how much that face is facing towards the light, basically. And then you can multiply that value by the light color source, and that means that faces that are facing towards the light are going to get more of that color than faces that are facing away from it. That's diffuse lighting. And then finally, the specular component is interesting because that's also relative to the view position, right? Like the shininess of an object. If you look at something shiny and you like move yourself around it, you're going to notice the highlights changing on the object relative to the position of your eye, right? So that's what we're simulating with specular lighting, which means that when you calculate it, you're calculating how much light is reflecting off of the surface into your eye, right? And then you put it all together and you multiply it by the input color of the object, and now you have a final lighting value. So that's a very basic Phong shader, and it looks cool. So we have different kinds of lights. There are directional lights. So classic example of a directional light is the sun. The sun is really far away and it's very bright. And so because the sun is so far away, all of the rays of the sun appear when they get to us to basically be parallel. That's not actually true, but it appears to be true, and it's close enough that if you just model stuff that way, it's easier to understand, it's easier to model mathematically. Like a directional light source is basically a light source that's coming from very far away, such that all of the rays of that light are directly parallel to each other. You have point lights. Point lights are closer in space, and they radiate in different directions. So like a light bulb is a classic point light. And so the rays of a point light are going to be different based on the position of the object, whereas that's not true for directional light. Then you have spotlights. Like a classic example of a spotlight is like a flashlight in like a first-person shooter game, and that's similar to a point light, except that you're going to truncate the rays based on the angle. So like a flashlight is only going to project rays out of itself at a certain angle. So it's very similar to a point light, but you just don't have a lot of those like 360 dimensional rays that are coming out of it. And so what if we want lots and lots of lights? Because again, if you look at this Phong shader that I wrote, the way that you render this is that like you have to render each object in your game through this shader, right, to light the objects. And if you have multiple light sources, you might have to expand this buffer a lot, so you could give it like 8 light positions and 8 light colors, and then you would add all of those lights together in the shader to get a final output. Or you could do different passes with additive lighting, but the point is that this is really expensive because every single object in your game is going to have to be rendered through all of the lights in your game for the lighting to look correct. And so to get around that, we have a method called deferred shading. It's very common. Basically, what I've described to you, where you have the lighting information directly in the shader, that is called forward lighting. And it's much more expensive than deferred shading. So instead, what you do with deferred shading is you have your geometry information, right? So all the cubes and 3D models, whatever. You're rendering all of that through camera space into a set of textures. And this is called the geometry buffer. So all of your information about the position of each of these pixels in space, their normal vectors, their colors, they're all rendered into the set of textures called the geometry buffer. And then when you want to add lighting, all you have to do is sample this geometry buffer, and then you have all of the information about that point in space specifically. And so what that means is you have much simpler light management. Your render pipeline is a lot easier to deal with because you just render all of the geometry in the game first, and then you render all of the lighting additively on top of that geometry. So to make that a little more concrete, let's say here we have like a little backpack model being rendered like 9 times in a row, and we have textures basically that are representing the position of these, because remember, textures are just data, right? So the color data inside a texture pixel doesn't actually have to refer to color. Like we can make it refer to other things, right? Like a position in space, or a normal vector, or albedo, which is a color, or the like specular highlights that are relative to that object in space. So this set of textures is called the geometry buffer. And then when you combine all of these into a lighting, into like output lighting basically. So when you run like your lighting shader, you basically say, okay, for this pixel, what position in space does this pixel represent? What was its normal vector? What color did it have? And then you can operate on all of those things without having to like re-render the object like over and over under these different lighting modes. And you just compositively add all of the lighting sources in one render pass. And it's much more efficient. You can literally have thousands of light sources, which would be completely impossible with forward rendering. So that's a really nice technique to have in your pocket. Shadow mapping. So what is a shadow? So shadow is basically just it's a point, like it's a set of points where light is not reaching, right? So what we're trying to calculate is like, you know, for an individual pixel on the screen somewhere, is light touching that pixel or is it not? And that's what shadow mapping helps you to calculate. So what you do is, like, let's say you have like a directional light source, like the sun. What you're going to do is you're going to render your scene from the position of the sun, right? And then for each point radiating out in the direction of the sun, that's going to give you a depth value, right? When you render the whole scene, now you have a depth value in your whole texture buffer, right? And then when you're doing lighting calculations, you can take that point and you sample it from that buffer that you've created. And if that depth value is closer than the one that you've calculated for that pixel during the lighting process, you know that something is in front of the light source, right? And that means that you don't have to shade that pixel, or you shade it differently based on the shadow offset. That's the basic idea of shadow mapping. I really recommend wrapping your head around this because it's really cool. You can do a lot of fun stuff with it. We actually developed like a 2D shadow mapping concept for Samurai Gun 2 that I'm going to show off. I think it looks really cool. I'm just going to rapid fire through these. Cube mapping. So the idea behind cube mapping is you imagine that you're in a big cube, right? And you have a direction pointing out from yourself to like the edge of the cube. That's what a cube map sample is going to be. So whatever that ray touches on the cube is going to be the color that you sample from the cube map. So you see like a diagram here, we've got a ray shooting out from the center of the cube, and it's going to touch like a pixel that's on the edge of the cube. So here's like a classic skybox cube map. So for skybox rendering, all you're doing is just sampling a cube map. You just imagine that you're in the center of the cube, and you have some rays shooting out from the cube, and you just sample like the edges of that cube map. Now you have skybox. The nice thing about that is you can actually draw the skybox, because remember I talked about rendering stuff forward to backward. So because the skybox is theoretically the thing that's like farthest away from you in a scene, you can just draw it last, and then none of these pixels that are like behind this cube that's in front of you have to get drawn. So that's a nice little optimization you can do. You can also use cube maps for reflection mapping. This is a screenshot from a game called Hunt Showdown. It's like a Western shooter set in the 1890s. You can see there's like a telescope mounted onto this gun, and we have this little section here in the scope, which is reflecting stuff that's behind the player, right? So what you do is you project all of the scenery in the game into a cube map. You render the scene from the perspective of this like reflection source, and then you have rays. Basically, like anything that's in this area is a light ray that's reflecting off of the scope and like into your eye, right? So that means that you have a direction that you can sample the cube map from. And so you just sample the cube map into the stencil area. Now you have reflection mapping. So you can do that for effects like that. Normal mapping. So I talked a little bit about normals. A normal, again, is just a vector that is perpendicular to a surface at a point. So a normal map is basically just texture information that has like normal offset information. So you can model the relationship of light on a surface more granularly. You can see in this comparison image that without normal mapping, you have this brick surface, but it doesn't really look like it has depth, right? Because the light is just projecting like uniformly over all of the supposedly shadowed areas. And so with normal mapping, you get much nicer definition because you're actually modeling the fact that the normals on the indents are different from like the flat normals that are on the surface. And like you can see on this diagram, that the normal map for each of these points is just offsetting the normal value of the surface, and then relative to the light position, you get different outputs. So on that note, physically based rendering is like a shading model that was actually developed by Pixar for their movies. And what it attempts to do is model the material interactions with the light in like a universal way. So instead of having to write like 10 million shaders for like all these different materials, surfaces that you're trying to model, you have one mathematical model that kind of bundles all of those things together into like a shading model. So the fundamentals of it are that you have albedo, which is sort of like the base color of an object. You have a normal map, which gives it like extra bumpiness. You have a metallic value, so it's basically does the surface at this point reflect light in a metallic way or in a non-metallic way, which has like different properties. There's roughness, which is basically like the surfaces of an object having like micro facets on it, right? So the more rough an object is, the more it's going to scatter light in different directions instead of just directly, and so it makes the surface look different. And then ambient occlusion, which is just like an extra shadowing factor that's on like certain parts of the surface. So you can see all of these 5 spheres in this image. These are all using the same shader, but they have different values for their albedo, normal, metallic, roughness, and ambient occlusion values. So it's really nice because you can model a lot of different kinds of surfaces without having to do like a million different shader variants that you have to configure. So here's one of those spheres being rendered. So these are 5 different texture maps, basically, that compose into this object through the PBR model. So like there's the albedo, again, which is the base color. You have normal maps, this is completely smooth, so the normal map is basically empty. And then you have metallic surface definition, a roughness surface definition, and ambient occlusion definition, and all of those compose. So you get kind of like a dirty looking like metallic sphere by like composing all of those things. And so this also lets artists like change the appearance of an object just by editing like texture data rather than having to do more complex calculations. So that's PBR. Again, it was developed for Pixar movies, which are pre-rendered, but you can also use the technique in real-time rendering, and lots and lots of game engines use this model. Unity uses it, Unreal uses it, it's everywhere. It's just really nice as like a universal shading model. The only downside to PBR, I would say, is that it does have a tendency, like because it's trying to model relationships of light and surfaces in a sort of like physics-based way. That's why it's called physically based rendering. It's trying to model like how objects sort of interact with light in the real world. The disadvantage of using this is that it kind of makes everything look the same, like vaguely realistic, and that might not be what you're going for with your game. You might want things that are more stylized, and if that's the case, you might not want to go with a model like this. Let's do a case study, because we've been talking a lot about 3D stuff, but a lot of games are two-dimensional. And you might think, oh, like 2D, like my Super Nintendo could do that. And remember I talked about specialized 2D hardware earlier? We don't have that anymore. All hardware is specialized for 3D now. So that means that 2D rendering is not inherently more efficient than 3D. It is possible to write horribly performing 2D renders if you don't know what you're doing. So for example, the naive case is that you just do one draw call per sprite. Every sprite is on its own texture, and you just draw each sprite one at a time. That's going to be awful. It's going to be so slow because you're texture switching for every single draw call. You might be switching the graphics pipeline for every single draw call. You might be switching the vertex buffer for every single draw call. It's going to be really, really slow. We call this like immediate rendering. It's really inefficient. What you want to do instead is batch this stuff, right? So you want to cram as many sprites as possible into a single mesh that you can draw as one draw call. So what you do is you batch sprites that are on the same texture page and use the same graphics pipeline. You bundle all of that stuff together, and then you can draw it all in a single draw call. So the process is that you start a sprite batch, which basically is just clearing data in the vertex buffer. You can submit sprites to the batch, and what that's doing is you're basically building this vertex buffer out of the sprite data. Each sprite has like a coordinate and an atlas for its individual texture data. You start the render pass, and then you draw all of your sprite batches once they've been built, and that means that for each batch, you bind a graphics pipeline, you call draw primitives on it, and it's going to draw all of the sprites in that batch in a single draw call. So as an example, here is the gameplay texture page of Samurai Gun 2. This is every single sprite that is ever drawn during gameplay in one giant texture. It's 4096 by 2048 pixels. You can see all of the individual, every single frame of character animation, all of the UI stuff, some of our big backgrounds that we have, they're all crammed into one huge image. And that means that we can draw tons and tons and tons of sprites in a single draw call. I'm going to demonstrate that in a minute here. Palette swapping is another thing we need for our game because it looks like an old 2D game, and we want people to be able to pick the same character without them looking the same. Old 2D game hardware, as I mentioned with my Super Nintendo example, had built-in palette swapping mechanisms. They just had like a color map that you could call into. We don't have that anymore. Nowadays we have to use textures and shaders. So the process that we use for our game is that we convert all of our sprites to grayscale. And then we have a palette texture, and the palette texture is always 256 columns and then one row per palette. And so basically what you do is you sample the grayscale value of that sprite, and that gives you the column that you should go into, and then the row represents the color replacement for that individual like palette texture, or for the individual palette draw. So you use the grayscale value in the palette row index, you sample into the palette texture, and then that gives you a final output color. So somebody in our Discord actually drew this because modders were wanting to add new palettes to characters, and they weren't really understanding how the process worked, and so somebody drew this diagram for them, and you can see that basically we have like a grayscale character here, and let's say that value is 128, right? And so then it's going to index into the 128th column, and then it's going to look at the color in that texture, and it's yellow. So now everything that's 128 gray is going to get outputted as yellow, and all of the black gets outputted as black because that value is black. Pretty cool, very efficient, one sample per draw. And so in comparison to this, so the old palette swapping mechanism, Bo's looking around shiftily, but he didn't actually write it. This is a palette swap shader that's been going around the game maker community for a really long time, and the way that it works is you have the first row of the palette texture is the colors that are actually in the sprite, and then each row is the replacement colors, basically. And so the way the shader has to work is it looks at the first color in the first column, and it's like, does the pixel I'm sampling from the sprite match this color? No. Okay, I'll go to the next one. Does this match? No. Okay, I'll go to the next one. Does this match? No. I'll go to the next one. So what does that mean? It means that until you have a matching color, you're doing n matching operations and n texture samples for each pixel. So that's literally, for drawing a single sprite, it might be sampling a texture literally hundreds of times. It was really slow, and I remember looking into this and being like, why is this game running like crap on old computers? And then I looked at the shader, and my eyes started bugging out of my head. So this is an example of how like doing things like naively in a 2D renderer can be insanely inefficient. That is way more texture samples than even like AAA games will be doing on like a single shader. It's crazy. Just don't do stuff like that. And then we have post-process effects. So we also call those like screen space effects. So those are effects that are operating after like most of the frame is already rendered. You're doing some final processing. Some examples of that are bloom effects or blur effects, chromatic aberration, which is like a CRT approximation effect, which like dilates the color channels in space. Screen space reflection for things like drawing like water, like reflecting something. You can do that in screen space. So like this is an example of like a bloom post-process. You have like the final frame, you extract like bright highlights from that frame, you blur that in two directions, and then you composite that back into your original frame. Now you'll get a nice bloom effect, and it looks cool. That's why people do it. So that's a post-process effect. You don't really need to understand like usually for doing a post-process effect, you're not operating on geometry in the scene. You're operating on it like after it's already been like bundled into a two-dimensional image, basically. So then I wanted to show off our game running through a tool called renderdoc. I'm going to do that right now. Before that, I'm going to talk a little bit about renderdoc. This is an absolutely essential tool. If you're writing any game, like any game with any kind of visual effect, you should be checking it through renderdoc. What it does is it captures, when it's rendering a frame through renderdoc, you can press the F12 button, it'll capture all of the data associated with rendering the frame. It records the history of each pixel calculation and each render buffer. You get a complete render state for each draw call in the game. You get a mesh viewer for like pre and post vertex transformations, so you can debug that. You can step debug vertex and pixel shaders. So if you have a really gnarly shader that's not working right, just run it through renderdoc and look at the actual step values, which you normally cannot do for a shader. Makes them very hard to debug. I cannot believe I ever wrote renderers before I used this tool. Like literally, it will find problems with your renderer in like 2 seconds compared to just staring at numbers for like days. Seriously use this tool. I'm going to demonstrate it in just a second here as we wrap up. Just wrapping everything all up, general performance guidelines for rendering. If you take nothing else away from this talk, take this away from it. You want to minimize the amount of render passes that you're doing. Again, doing stuff, expensive. Not doing stuff, not expensive. So don't do stuff. You want to batch stuff aggressively. The fewer times you're changing the render state in the middle of your frame, every time you change the render state, the graphics card has to load or unload memory or like flip switches or whatever. The fewer times you have to do that, the faster your render is going to perform. You want to avoid overdraw whenever possible. If you're rendering a pixel and then rendering something directly over it that completely changes the color, that's a complete waste of time. Again, not doing stuff cheap, doing stuff expensive, don't do stuff. You want to cull stuff aggressively. That's part of what I'm talking about, like depth culling, for example, stencil culling. Again, executing shaders, filling pixel memory, not free. If you can avoid doing that, draw stuff front to back, do stencil cutouts. Avoid synchronization points. That's what I'm talking about. Remember, the CPU and the GPU are on completely different timelines. You don't want the CPU to ever have to wait for the GPU to do something. You don't want the GPU to ever have to wait for the CPU to do something. Make sure that they are running correctly in parallel. And then in shaders, you can just avoid branching or other like expensive operations like long loops or things like that. Don't do that in shaders. The faster the shader runs, the faster your frame outputs. Right, so before I do my renderdoc demo, I just want to do a few acknowledgments. I took a lot of these diagram resources from learnopengl.com by Joey DeVries. It's an amazing resource. It's called Learn OpenGL. And technically, he does everything in terms of OpenGL, but all of the techniques he talks about can be used in any rendering system. It's a very in-depth explanation of everything you need to know about the rendering process. It's amazing. If you have any questions about anything, always go to learnopengl.com first. It's amazing. Thank you to Baldur Carlson for developing renderdoc. It is the most incredibly useful tool for anybody writing a renderer. Just don't leave home without it. Shader Toy is a really nice little website for programming like screen space shaders. People make amazing stuff on there, but it's a really nice little tool for like quickly demonstrating an idea or trying to like hack something out without fitting it into your entire render pipeline for your game. Thank you to the FNA 3D teams and Samurai Gun 2 teams for letting me tinker on stuff all the time, develop all of these ideas. So I'm going to talk about renderdoc really quick. So let's get renderdoc open here. This is what renderdoc looks like. We run a program through it. So I'm going to load current build of our game through this. That's not the right sounds, but Okay, so for example, we have a dynamic lighting system in our game, so one of the passes involved in doing that is drawing everything that's going to block light into a texture. So that's what you see with this process. Those are all of the light blockers in the scene. And then similarly, we have all of the light receivers in the scene that are being rendered on 2 different render passes. This is all of the normal values for each of the rims being written into a texture so that we can do rim lighting calculations on the scene. And then this is the actual color data being rendered out. So we have some black lines being rendered that you don't really see, and then grass, and then ground terrain, and then background terrain, and then skybox 2D, characters being rendered, bamboo. All of these are individual draw calls. And then here you can see, this window so small. It doesn't matter. So you can see this is the rim lighting calculation. Right there. So this is before the rim lighting, and then you see the rim lighting happening right there. So now if we go into the pipeline, this is a breakdown of the whole graphics pipeline that I was telling you about. So we have vertex input, we have the vertex shader, which we can look at the actual code for that. We have the rasterization process and all of the configuration of the rasterization. And then we have the fragment shader, which we can also look at all of the code for that. This is the lighting shader that's currently running for that draw call. And then finally the frame buffer right, and this is going to tell us what the blending state is, and what the depth state is, and what the stencil state is. So as you can see, like this is like the whole like window into the graphics state of the program when it's doing this draw call. Amazingly useful for debugging. We can look at the triangle data that's being used in these calculations. Let me look at a more complicated one. So this is the terrain buffer for the game that's drawing all of our like sprite tiles basically that make the level look cool. You can see that's actually a 3D model that has been built. That is depth. So stuff that's farther away is farther behind. So even though this is a 2D game, all 2D games are actually 3D. All rendering hardware is 3D now. And if you manipulate the fact that it's 3D, you can get some nice optimizations out of that. So we actually just bake all of the terrain data into like a giant 3D mesh when the game loads, and then we don't have to rebuild it every frame. And you can look at that through the mesh viewer. So if you were making like a 3D game and like you were rendering like 3D models of characters and stuff, you would be able to look at those in here. And you can look at it after it's been transformed by the vertex shader into screen space. This is what it looks like. You can look at each individual vertex. Those are the texture coordinates right there. So if like stuff is going weird, you can literally just look at the data values and see like what's being spit out by the vertex shader. So yeah, again, I could probably teach a whole class on using renderdoc. It's amazing. But if you have any rendering problems with your game, shove it in here, learn how to use it. You will debug stuff so fast. It's amazing. That's it.